can look into some chips that realizes these multiplexers. For example, this 74157 chip. So, it has got quad 2 input multiplexers. That means, it has got in the chip there are 4 multiplexers. So, if this is the full chip, so there are 4 multiplexers. Okay. So, they are all 2 input multiplexers. Okay. There are 4 such multiplexers, and these multiplexers, so they have input A0A, A0B. So, I0A, I0B, I0C and I0D as the 0 inputs, and I1A, I1B. So, in the first multiplexer, so this is multiplexer number 0. So, it has got I0A and I1A as input. The second multiplexer, the multiplexer 1. So, it has got I1A and I0B, and it has got I0B and I1B. So, that way so there are 4 multiplexers, one is A, B, C and D. So, any multiplexer, it has got the, so the multiplexer A, it has got input I0A and I1A, multiplexer B, it has got inputs I0B and I1B. So, like that, and the select lines are same. So, for all of them, so there is one select line only. So, we can just the select line and the enable line, so they are common for all the multiplexers. So, we will see how this is working. So, the for that we need to look into the corresponding truth table. So, this is the symbol that we have. So, there is a select line, there is an enable line. So, for this multiplexer quad multiplexer to operate, this E line must be equal to 0, then only this multiplexer will operate. Now, so this is actually the E bar. So, if E bar equal to high, then irrespective of the value of S, the select line, so all these outputs are equal to low. However, if if E bar is low, that is then active enable signal is given to 74157, then if the select line is low, then in the YA output, so I will get I0A, in the YB output I will get I0B, YC you get I0C and YD I will get I0D. So, essentially you can say that the structure is something like this. So, I have got 4 multiplexers. So, I have got 4 multiplexers connected like this. Okay. So, I have got these 4 multiplexers, and then the first multiplexer has got I0A and I1A, I0A and I1A. The second multiplexer has got I0B and I1B. Third multiplexer has got I0C and I1C, and the fourth multiplexer has got I0D and I1D. And for all these multiplexers, the select line is same. So, that is coming from S. So, that is the select line. So, that is same, and this output is called YA, this output is called YB, this output is called YC, and this is called YD. Okay. And there is an enable line, of course. So, this is the structure, logically this is the structure that we have inside the inside the chip. Now, so E bar input is low, it allows the selected input data to pass through to the output, and E bar input is high, it will disable all the multiplexers and all outputs will be low. When E bar equal to 0 and S equal to 1, the Y outputs will follow the set of I1 inputs, where YA equal to I1A, YB equal to I1B, etc. Similarly, when S equal to 1, it will be following the 0 input. So, in that case YA will be I0A, YB will be I0B, like that. So, that is the standard multiplex. Okay. Now, we will be looking into some technique by which we can realize some logic circuit function using some multiplexers. So, we will take as an example 74151, which is an 8 input multiplexer. So, it is 8:1 multiplexer, we can say. So, we normally we also for the multiplexers we write it like 8:1 multiplexer, that is that there are 8 input lines, 3 select lines and one output line. Now, what we do is that, so this is, suppose this is the function that we want to realize. So, this is a combinational function, 3 input combinational function. So, for the combination 0 0 1, 0 1 1, 1 0 1 and 1 1 0, the output should be 1, and for the rest of the places the output will be 0. So, what we do first for doing it, for realizing the circuit is that we note down the corresponding decimal value of the different min terms. Okay. So, the first min term is 0, second is 1, third is 2, like that. Now, we note down the places where the value is equal to 1, and accordingly we get the circuit. Like here you see that this function can be realized like this. So, what this enable line is made low, so that this multiplexer is enabled. Now, this A0, A1, A2, so they are connected to the select lines of the multiplexer. Okay. So, 0, 1 and 2, and then if you look into this place, you see for 1, 3, 5 and 6 the output is 1 and rest are 0. For 1, 3, 5 and 6 it is equal to 1. So, for data input 1, 3, 5 and 6, so they are tied high, and this data input 0, 0, then 2 and 4 and 7. So, 0, 2, 4 and 7, for them it is low. So, it is for 0, 2, 4, 7 they are tied low. Now, the way it operates is, if you apply some value here A0, A1, A2, some pattern here, depending upon the value, one of the input lines will, one of these data input lines will be selected to the output, and if it happens that it selects a line from this 1, 3, 5 and 6, then you will get a high here or 1 here. But if it selects the values are such that it is selecting one of these data inputs 0, 2, 4 and 7, then you will get a 0 there. So, this way using this multiplexer we can realize any combinational logic. Okay. So, we can just what we need to do is, some of the data inputs are to be tied high, some of the data inputs are to be tied low, and these combinational function variables, so they should be tied to the select lines of the function or select lines of the multiplexer, and definitely the enable line has to be activated. Okay. So, how can I do these things? So, this whole operation, so it can be summarized like this. So, this is an efficient method for implementing Boolean function of n variables with a multiplexer that has n minus 1 select input and one that is and 2 power n minus 1 data input. So, it is like this, that in this previous example, what has happened is that I have got 3 input, it is a 3 input function. Okay. So, this is a 3 input function, and for that we needed one 8:1 multiplexer. So, but if I do that, then what happens is that many times the multiplexer size becomes too high. For example, in my library, or I may not have these 8:1 multiplexers available, maybe only 4:1 multiplexers are available. That means what is needed is, I need to do this thing, I have got a 2 power I have got an n variable function, but I will be realizing use them using multiplexers that has got n minus 1 select lines, that is 2 power n minus 1 data lines. So, what we do for this is that we first make the truth table, and the first n minus 1 variables of the table, so they are connected to the select inputs of the multiplexer, and for each combination of select variables evaluate the output as a function of the last variable, and accordingly we put the variable as 0, 1 or the variable itself. There is an example. So, suppose this is the function that is given to me. So, f x bar y bar z plus x bar y z bar, so plus x y z bar plus x y z. So, what we do? We have got so this is a 3 variable function. So, you can straightway realize it using 8:1 multiplexer. So, like this, so I can do it in this fashion using an 8:1 multiplexer. So, this select lines, so I apply x, y and z, and these data lines. So, these are the data lines. 0, 1, 2, 3, 4, 5, 6 and 7, and then I know that for 1, 2, 6 and 7 the output should be 1. So, for 1, 2, 6 and 7 I tie them together to logic high. So, this is tied to logic high, and 0, 3, 4 and 5 they should be tied to low. So, what I do, I take these lines and tie them to low. So, this is made 0. So, this way using, so this is my function, this is my f. So, by using this 8:1 multiplexer, so I can definitely realize it, but how can I do it using 4 input multiplexer? Okay. So, for doing it with 4 input multiplexer, so we have to proceed like this. So, we make the truth table, and then we first this x and y. So, these inputs we apply directly to the select lines S0 and S1, and for the third input I figure out like this first. So, if I look into this first two terms, so 0 0. So, whenever this x y equal to 0 0, that forms one group, then 0 1 it forms the second group, 1 0 x y equal to 1 0 forms the third group, and 1 1 forms the fourth group. So, these are the 4 data inputs, like this will correspond to the input pattern S0 x y equal to 0 0, this will correspond to 0 1, this will correspond to 1 0, and this will correspond to 1 1. Now, if I look into the portion of the truth table where it is 0 0, so that portion of the truth table, and if I do a minimization in terms of the third variable, so I will get f equal to z. So, that way in this line I apply z. Next, for the this is 0 1, for x y equal to 0 1, so I get here as z bar. Okay. So, if you look into this function here, so that is z bar. So, that is I am getting as z bar. Then this part is all 0. So, it is 0, and it is all 1. So, this is again 1. So, I take a 4:1 multiplexer, then of course, I need some additional circuitry. So, what is actually needed, we were needing is, apart from the multiplexer, I need an inverter here for getting this z bar. Okay. For getting this z bar I am needing another inverter, but otherwise I can do it like this. So, this way you can realize circuits using different number of multiplexers. For example, if I want to do the same thing using 2:1 multiplexer, then what to do? So, it is using 4:1 multiplexer. So, if I have to do it using 2:1 multiplexer, then this 2:1 multiplexer, it will have only one select line and two data lines. Okay. So, on this select line I apply x, okay, and these data lines are 0 and 1. So, I partition this truth table into two partitions. So, in one partition x equal to 0, other partition x equal to 1. Now, if I do a minimization, you see that here the function that I am getting is in this part. If you look into this part, the function that I am getting, so it is 1 when only one of y and z are equal to 1. So, this is nothing but y XOR z, and in the lower part, I am getting the function for this part. So, whenever this y is equal to 1, the output is equal to 1. So, for this part I have got the function y. So, what I can do, I can apply y here, and I can take one XOR gate, and take this y and z inputs to the XOR gate. Okay. So, I can do it like this. So, this is my f. So, this is using 2:1 multiplexer. So, in this way you can have this multiplexers of lesser sizes to realize these combinational functions. Okay. So, if you are having same, if there is an n variable function, and if you have got a 2 power n:1 multiplexer, then it is straightforward. As it is reducing, then you have to do the grouping of these terms, and accordingly you have to get the truth table, you have to get the multiplexer realized. So, next we will see, so two variables x and y are select lines. So, this is the thing that we are discussing. When x y equal to 0, f becomes equal to z. So, we have also seen the two input multiplexers like that. So, this is another example where I have got this 4 variable function a bar b bar c bar d plus a bar b bar c d plus a bar b c bar d, and this I want to realize plus all this. So, this is a 4 variable function. So, I will need a 16:1 multiplexer if I want to do it directly. So, if I want to realize it using 8:1 multiplexer, then we can do it like this. So, we are applying this A B C to the select lines of the 8:1 multiplexer, and then we are dividing the truth table into regions of similar values of A B C. So, first part A B C values are 0 0 0 and second part is 0 0 1 like that. And if you look into the corresponding function f, then for the first part f equal to d, second part also f equal to d, third part f equal to d dash, then f equal to 0. So, it goes like this. So, I can take help of a few lines and inverters to feed the data lines of the multiplexer, and accordingly I can get the 4 input function realized using 8:1 multiplexers or 8:1 multiplexer. So, this way we can use multiplexers to realize logic functions. So, another technique by which we can realize this multiplexer based circuit is where we do not go for higher degree multiplexer, but many times we want to realize the circuits using 2:1 multiplexers only. So, if you want to do that, say I have got some function f which is a 3 variable function. So, x, y and z, and this is the function is given by say x, y plus x bar z like this. Okay. Now, if you want to realize it using 2 input multiplexer, then we can do it like this. So, there is one decomposition which is known as Shannon decomposition. So, this Shannon decomposition in the most generic form, it tells that if I have got an n variable function x1, x2 up to xn, then this can be decomposed around the variable xi, and the decomposition is given by xi bar into f, where these other variables remain unchanged, only xi is said to be equal to 0. Okay. Xi is said to be equal to 0, and then plus xi into f of x1, x2, xi equal to 1, xi plus 1, xn. That means, in the function f you put xi equal to 0 in one case and xi equal to 1 and in the other case. So, in both the cases the function f reduces to a function of n minus 1 variable, because one variable has been fixed to some constant. So, that variable is gone. So, you have got a function of n minus 1 variable, and then we put it as xi bar into f x1, x2 up to xn with xi equal to 0, and then plus xi into this. So, this is known as Shannon decomposition. So, if you apply the Shannon decomposition, so essentially you see what happens is that if I have got this function f, then if I have got a 2:1 multiplexer, then I can do it like this. So, this is the input 0, this is the input 1, and here in the select line I apply the variable xi, and when xi equal to 0, so here I have to somehow realize the function, the first function x1, x2, xi equal to 0 up to xn, and here I have to realize the function x1, x2, xi equal to 1, xn. Then again this function can again be decomposed using Shannon decomposition around another variable. Okay. So, so that way it goes on. Okay. So, let us take an example, say this function that we are talking about. So, if we decide that okay, okay, we will decompose it around a single variable say x, then what happens is that f x y z, it can be written as x bar into f, where I put x equal to 0, y z plus x into f x equal to 1, y z. This is from the definition of that Shannon decomposition. Now, in this function, if I put x equal to 0, so what you get is z. So, it tells that it is x bar into z, where z bar is this function, and it tells that if you for the second case if you put x equal to 1 here, so you are getting y. So, this is x into y. So, it tells that you take a multiplexer 2:1 multiplexer, and then if you apply x as the select line, then you will be getting the. So, you apply so this is 0 and this is 1. So, you apply z here and y here. So, this is the realization of the function using 2:1 multiplexer. Now, if somebody instead of taking x as the variable around which we decompose, so take say y as the variable around which to decompose, then what happens is, so it gets a function realization as f x y z equal to y bar into f x y equal to 0 z plus y into f x y equal to 1 z. So, that is y bar into, if I put y equal to 0 here, so I will get the function x bar z, and then if I put y equal to 1, then this gives me x plus x bar z. So, that is nothing but x plus z. So, here I am getting x plus x bar z. So, by Boolean algebra, so I can say it is y into x plus z. So, it says that at the top level you have got this realization. If you apply y as the control input, select input, then you have got. So, here I need to realize the function x bar z, and here I need to realize the function x plus z. So, we do the same thing now on this x bar z, we apply Shannon decomposition. So, if I apply Shannon decomposition, then if I select x as the select line, if I put x as the select line like this, if I put x as the select line, then when x equal to 0, so this is z, and when x equal to 1, so this is 0. So, I can do it like this, and for realizing this x plus z, again I can do it using Shannon decomposition around x. So, when x equal to 0, so this is z, and when x equal to 1, this is 1. So, this 2:1 multiplexer based realization, so it realizes the same function as this one, but you see depending upon the variable around which you have decomposed in Shannon decomposition, in one case you need a single multiplexer, in another case you are requiring 3 multiplexers. So, that can happen. So, that way any n input function, it can be realized using only 2 input functions. Okay. And this whenever I am requiring say some complemented input also. So, sometimes so you can also do it using this input say inverter also, like whenever we are having a 2:1 multiplexer. So, 2:1 multiplexer the function that we have is say x, y, and this is the select line s, this is the output f. So, f is given by s bar x plus s y, s bar x plus s y. Now, you can use this structure to realize AND gate. How? So, if for AND gate I want that if I have got 2 inputs A and B, it should produce a 1 here. So, you see that if you it should give me the function a b. So, you see that if I apply a at s, if I apply A at S and B at Y, and if I make this x equal to 0, then this function transforms to something like this. So, S bar, that is A bar into 0 plus A into B. So, A bar into 0 is 0. So, you are getting A B. So, this way I can realize one AND gate using this multiplexer, 2:1 multiplexer. Can I get an OR gate? So, for getting OR gate, OR function, what I need is A B, and this F should be A or B. This A or B is can also be written as A or A bar B. So, we have seen that these two expressions are equivalent, A plus B and A plus A bar B. So, what we do in this case? So, if I take this S as A, okay. So, if I take say y equal to 1, so I have got this expression f equal to s bar x plus s y. Now, if you try to draw the if I put this y to be equal to 1, then this expression turns out to be s bar x plus s. Now, if you set this s to be equal to A and this x equal to B, then this is nothing but A plus A bar B. So, what I essentially get is that if I have a 2 input multiplexer, then on the line x I put B. So, this is 0 and 1, sorry, 0 and 1, and this is my S. So, on the 0 line you put B, and on this y, so on the y input, so this is 1 and this is equal to S, this is equal to A, S equal to A. Now, the function that you get here is f equal to A bar B plus A, that is nothing but A plus B. So, I can get this OR gate also realized. So, can I get an inverter? So, if I have got this function, okay. So, now this S, so this is 0 and this is 1. Now, you see that if I when S is 0, the output should be 1. So, I make it 1 here, and I take an I take the multiplexer, and then the 0 input I connect 1 and 1 input I connect 0. So, accordingly I will get here output function f as S bar into 1 plus S into plus S into 0. So, that is equal to S bar. So, I am getting the inverter also. So, I am getting AND gate, OR gate and the inverter. So, this 2:1 multiplexer, so this is also an universal logic element. So, it can realize all the logic circuit that we can think about. Okay. So, this is another universal logic element. Apart from the NAND gate, NOR gate that we have seen, this 2:1 multiplexer is also an universal logic element.